last time in chapter 20 we left over here, we're going to move on as part 2. Oxidation of primary alcohols to carboxylic acids. You can take primary alcohols and react them with bichromic acid in the form of sodium dichromate or NaOCl. That will oxidize to the aldehyde and then get further oxidized to the carboxylic acid. In addition, potassium permanganate can be used, but the yields are often lower. You can also take alkenes, cleave alkenes using KMNO4 concentrated. This will generate the glycol, which will then subsequently go on to the acid if it has an H on one side. Alkynes are cleaved using either ozone or KMNO4, ozonolysis meaning, or KMNO4. Again, in this case, the diketone is generated, and then that subsequently becomes the carboxylic acids. You can do side chain oxidation of alkyl benzenes, any alkane coming off the benzene. It doesn't have to be linear, and it could be of any size. When you subject them to sodium dichromate, sulfuric acid and heat, or potassium manganate, water and heat, you'll take your alkyl group and convert that into a carboxylic acid. You can take Grignard reagents, so here's alkyl halide, make it into a Grignard. This then reacts with carbon dioxide. Again, nucleophilic attack, and then this will generate the carboxylate, and then in the presence of protonated water, it'll generate the acid. This reaction is sometimes called CO insertion, and essentially increases the number of carbons in the molecule by 1. Nitriles, you can react alkyl halides by SN2 reactions with sodium cyanide, and then this will generate your nitriles in the presence of protonated water or basic water. You can generate the carboxylic acid and the ammonium cation. The overall reaction, starting from the alkyl halide, essentially adds an extra carbon to the molecule. An important thing to note is that oxidation of alcohols does not change the number of carbon atoms. Oxidative cleavages of alkenes and alkynes decreases the number of carbon atoms, except in cyclic cases, and carboxylation of Grignard reagents and formation of hydrolysis of nitriles increase the number of carbon atoms by 1. Acid derivatives. Group bonded to the acyl carbon determines the class of compound. So if it's OH, it's obviously the carboxylic acid. If it's a chloride, it's acid chloride, OR, ester, NH2, amide. And these interconvert via nucleophilic acyl substitutions. In nucleophilic acyl substitution, you have an acid chloride or an acid halide, and your nucleophile comes in, attacks the center carbon, electrons go up to the oxygen, forms a tetrahedral intermediate, those electrons come back down and then kicks out the halide to generate your acid derivative. Your carboxylic acids react by this nucleophilic acyl substitution, where one nucleophile replaces another on the acyl carbon atom. So here's an example. Nucleophilic attack, electrons go out. This is the basic hydrolysis of ester. Again, forms a tetrahedral intermediate, then electrons from the oxygens come down, and this is a better leaving route to kicks it off, generating the acid and alkoxide. Now that you have the acid and the alkoxide will take off because this is a good acid. It'll deprotonate, forming the carboxylate and the alcohol. Fischer esterification, you have your acid reacting with an alcohol in the presence of acid to generate your ester and water. The mechanism of this I've spoken to you in previous chapters. And so some examples would be, here's an acid, here's an alcohol in the presence of sulfuric acid generating the ester. This is a dicarboxylic acid. In the case of excess methanol in acid, you generate the dimethyl phthalate. here reaction is an equilibrium. So the yield of the ester isn't high, so to drive the equilibrium towards the formation of products, you use a large excess of alcohol. An important thing to note is that in equilibrium reactions, look for ways to use excess of reagent, or else to remove a product as it forms. Is it possible to use one of the reagents as a solvent? That's one thing. Can we distill off a product or drive off water? That's another thing that you can do to push the equilibrium towards product. In the mechanism of Fischer esterification, it's all done in the presence of acid. So the first step is protonation. Once you protonate, then the alcohol attacks, electrons go, quench that positive charge. Now you have this tetrahedral intermediate in which alcohol will come and deprotonate, so it quenches this positive charge. And now you have these ester hydrate. Once you generate the ester hydrate, one of the oxygens will protonate, forming a good leaving group. So now you have electrons from your oxygen here come down, kicking this off. It's still protonated, and so another equivalence of alcohol will come and quench that positive charge, generating your ester. So you're asked in this problem to hydrolyze ethyl orthoformate and dilute acid to form formic acid and ethanol. So the first step is protonation. This will generate a great leaving group, and instead of it just leaving, you can have it attack as it's leaving. This will generate the product over here with the water now attached. We can deprotonate that so that it's just the alcohol generating the product here. And then the next step is for another OET to come and protonate. This is also a good leaving group, but at the same time, electrons from your oxygen here will come down, right? Forming this protonated ester. And then you have water deprotonate, neutralize to form the ethyl formate. And then you'll do another equivalence of water in which your H2O, so that you have it, will come in, attack, electrons will go to the oxygen, and then you have HCO minus, OHH plus, and OET. And so then from here, your OET will take off a proton, electrons will go here, so now you have HCO minus, OET, OH, electrons will come down, kick this over, sorry, it has a H attached to that since we did the transfer, so this leaves, and now you have HCO, OH. Next thing is esterification using diazomethane. So you can take an carboxylic acid, add diazomethane. This will generate the methyl ester and nitrogen as a gas. This usually produces quantitative yields of the ester, and diazomethane is very toxic, explosive yellow gas, so you have to be careful when you're doing this reaction. So the mechanism involves your diazomethane, in which your electrons from your nitrogen can move in resonance. Once you have your electrons on the carbon, it deprotonates, forming carboxylate and the methyl diazonium ion. Here now it attacks. The carboxylate attacks the methyl, kicking the electrons to the nitrogen, forming nitrogen gas, and then the methylated, or the ester. You can synthesize amides. Your acid and your amine will generate deprotonated carboxylate, ammonium carboxylate salt, and then in the presence of heat will generate the amide and water, so forming the the product that we're interested in. You can take acids and reduce them in lithium aluminum hydride, followed by protonated water to generate the primary alcohol, or borane can also reduce BH3, can also reduce carboxylic acids all the way down to the alcohol. Acid chlorides, you can use lithium aluminum hydride with OTBU. This, you'll have a source of hydrides attack, essentially, electrophilic carbon, electrons go to the oxygen generating this product. Then the electrons come down and kick out the chloride to generate the aldehyde. So if you wanted to actually generate the aldehyde from the acid, you can just take the acid, convert it to the acid chloride by SOCl2, and then reduce by the lithium aluminum tert butoxide moiety here. You can take carboxylic acids and, in the presence of organolithiums, generate the ketone. It's organolithium's 2 equivalents, and then water will generate the ketone. So the mechanism is first lithium will come in, deprotonate, generating the alkane and the carboxylate. The second lithium will come in and attack the carboxylate and then generate the dianion, shown here. Once the dianion is generated, then you're subjecting it to the second step of protonated water, in which now you exchange lithiums with the hydrogens, and then you have the ketone forming, in which electrons here come down. This will also will make it positively charged so that it's a good leaving group, and it'll kick off the water to generate the ketone. Acid chlorides, you can take a carboxylic acid, subject it to thionyl chloride or SlCl2 or oxalochloride, CoCl2, and here is your mechanism for that. Oxygen will first attack the thionyl chloride, electrons go to the oxygen, generating this intermediate. This undergoes resonance, in which you have electrons from your oxygen come down, quench that charge, and then you have electrons from the oxygen come in, kick off the chlorine. The chlorine will then pluck off that protonated carbonyl, generating the chlorosulfite and anhydride. Then the Cl- will come in, attack, electrons go to the oxygen, the electrons from the oxygen come down. This is a good leaving group, forming SO2 and then Cl- and your product. You can generate an ester by much more easily by taking the carboxylic acid and converting it to the acid chloride and just subjecting it to reaction with alcohol, because this is a good leaving group. You'll just have attack, right? Electrons come up, electrons come down, kicking that out. And this is better than the Fischer esterification process. Amide synthesis, you can take an acid chloride and an amine, and you can generate an amide. Again, electrons will come, attack the carbon, electrons will go up and down and kick off the chlorine to generate the amide under basic conditions, because it generates acid, and to kind of push this forward, if you add sodium hydroxide, then it'll generate the salt and water. And so this ends part 2 of chapter 20.